In this video, we're going to talk about flow networks. Consider the following graph. Suppose this is a network of pipes that water is flowing through. And we can assign a flow to each pipe, or the flux, or the gallons, the number of gallons of water flowing through the pipe every minute, or something like that. So we could assign a flow of 5 to that edge, maybe a flow of 4 here, 1 here, say 3 here, and 4 here. Now look at the vertex labeled S. That's going to be the source. That's the source of the water. The water is coming out of the source. And then we have the node, or the vertex labeled T, which is the target, and that's the sink. That's where the water is ending up. You can think of it as a reservoir. So we have water flowing from the source to the sink. Now, notice how many gallons per minute are flowing out of the source? Well, 8. And how many gallons per minute are flowing into the sink, or the target? Well, 8. So this is a system where we have the exact same amount of water coming out of the source as in the sink. If it was any different, then we would have some other source or other sink somewhere in the network. Now, notice that we have, let me change colors here. We have 5 gallons per minute flowing out of here, and then it splits, right? We have 1 gallon per minute going that direction, and 4 gallons per minute going that direction. So notice that that vertex has the same amount of water coming in as it has going out. We could change it. We could say we want to have 2 gallons of water coming there, and in which case we would have to lower this to 3. So we still have 5 gallons per minute going in, 5 gallons per minute coming out. Now, we can also assign what we call a capacity to each edge, or to each pipe in this example. We could say that, let's change colors here. This edge this pipe has a capacity of, say, 7. And this pipe has a capacity of 8. This pipe has a capacity of 2. This pipe has a capacity of 4. And this pipe has a capacity of also 4. Now, what if the flow exceeds the capacity? Well, that doesn't make any sense. Then it's not valid. The flow can only go up to the capacity. So if I wanted to do the same thing I did before and increase this flow to be 2, that's legitimate. I can do that. I just have to decrease this flow so that 2 plus 3, which is the outflow from that vertex, is equal to 5, which is the inflow. I can do something else too. I could change this 5 to be 6. It's not exceeding the capacity. I just have to adjust the outflow to 4. 6 equals 2 plus 4. Inflow equals outflow. Now, can I increase this flow here? Can I increase the amount of water going through that pipe? No, because I can't increase the outflow from that vertex. I can't increase this because it would then exceed the capacity. Okay, so this is a flow network. Let's formalize some of these ideas. S is the source. T is the sink. The graph is directed. So these are properties of a flow network. All edges are labeled with a flow function value. And that's going to be less than the capacity. Okay, so F here is the amount of flow. So that would be like the 3 there or the 4 there. And the capacity is the 4 or the 7. And so our flow cannot exceed the capacity. Furthermore, the flow must be greater than or equal to 0. We also have to have what's called flow conservation. What that means is this. Okay, the notation is a little bit funky. This represents the flow into V. So the flow from every neighbor U, or every vertex U, into V. This is the total flow from V, or it's the outflow. And this is the inflow. So this is the flow conservation is just a fancy way of saying that the amount of material coming into a vertex has to equal the amount of material coming out. That's flow conservation. We have another similar property in a flow network, and it's this. So this is the flow out of the source. And this is the flow into the sink. And those have to be equal. It turns out that flow conservation and this right here are identical. They're equivalent to each other. If flow conservation is satisfied, then we're going to have the same amount coming out of the source as we have going into the target. Oh, and one other thing. Flow conservation except for S and T. Forgot to mention that. Let's bring up a figure from the book. This is 710.1, or on page 710. Okay. This is in the book they talk about this company, Lucky Puck Company. They make hockey pucks, and their factory is in Vancouver, and their warehouse is in Winnipeg. So they want to be able to ship hockey pucks from Vancouver to Winnipeg. And so what this is it's a flow network, and the numbers are the capacities on the edges, and those represent the numbers of crates they can ship. So for example, they can ship 16 crates of hockey pucks from Vancouver to Edmonton every day, and 14 crates from Calgary to Regina. And so what they want to do is, given these constraints, given this flow network, they want to be able to maximize the number of crates they can ship from Vancouver to Winnipeg. If they can only ship, 20 crates per day, it doesn't make any sense to produce 25 crates per day because they wouldn't be able to store them. Okay, so let's look at some of the properties of flow networks to see if this satisfies it. Now, what we're looking at here is just the capacities. So we can ship 16 crates from Vancouver to Edmonton every day. That doesn't necessarily mean that we will. And so that brings up the second figure, which shows both capacities. So here's the capacity for Vancouver to Edmonton. And here is the actual flow. We're actually going to send 11 crates per day from vertex S to vertex V1, which correspond to those two cities. So let's look at some conservation. So let's look at V1. What is its inflow? Well, we have 11 crates per day coming in and 1 crate per day. So we have 12 crates per day coming in and 12 crates per day going out. Let's look at V4. So we have 11 crates per day coming in and 7 plus 4 crates per day going out. That satisfies conservation. So we could do that for every vertex, and we would see that this is a conserved system. Now, what is the value of the flow? Now, up here, I said bar F bar. So that is actually the value of the flow. And that's the value of the flow is the flow coming from the source or the flow going into the sink. So let's look at the value of this flow here at the bottom. Well, we have 11 coming out of S and 8 coming out of S. So the value should be 19. Let's just confirm that with the target. 15 going into the sink plus 4 going into the sink, and that's 19. So yes, the value of the flow is 19. So the big question is, how many hockey pucks or how many crates of hockey pucks can we ship from every day from Vancouver to Winnipeg? Well, we can look at the capacities, and if you just look at the capacities, let's change colors here. Coming out of Vancouver, we can send 16 coming out there and 29 coming out there. So you think, oh, okay, well, I'm just going to, or not 29, but 13. So you could say, well, I'm going to ship 29 crates of hockey pucks every day from Vancouver. But the problem is, Winnipeg can only accept 24 per day. And so we can't ship 29. We can ship at most 24. So we say, okay, well, let's ship 24. But then you have to consider actually the whole network. You have to think about where there might be bottlenecks. For example, suppose we have a network that looks something like this. This will be an extreme example. Now, suppose our source, we have, say, 5, 5, and 5 coming out of the source. These are capacities. And 15 going into the target. So here's our source and here's our sink. So you might say, okay, well, I can have a flow capacity of 15. But what if we only have this? So this node, this vertex right here is a bottleneck. So it's not totally simple to be able to maximize our flow. Okay, before we start talking about maximizing our flow, let's talk about whether we have multiple sources and sinks. I'll bring up this figure. This is on page 713 of the book. Now look at the graph on the left. You can see we have multiple sources, S1, S2, S3, S4, and S5. So that could be like multiple factories that are manufacturing hockey pucks. And then we have multiple warehouses. Now, in a flow network, we required that there only be one source and one sink. And so how can we handle this type of a network? We still want to maximize our flow. Well, it's as simple as adding a source, a single source, with infinite capacity to any of the other sources, and adding a sink with infinite capacity from any of the previous sinks to that sink. And that's how we can create a flow network out of one with multiple sources and sinks. This S is called a super source, and this T is called the super sink. Awesome names, I think. Okay, now the question is, how can we maximize our flow? So let's consider a very simple network. Very simple flow network. And let's give it some capacities. 4, 3, 1, and 2. Now I want to maximize the flow from the source to the sink. If I looked at just the outgoing capacities from the source, I would say I can have a flow of 5. And the incoming to T, I would say, oh, I can have a flow of 5. Well, then can I have a flow of 5? Well, it turns out that I can't, because if I look at this capacity here, if I say, well, I'm going to give it a flow of 4, then the outgoing flow from this vertex here can only be 3. I can't have an outgoing flow of 4, and that doesn't obey the property, the flow conservation property of flow networks. So I can only have a flow of 3 there and 3 here, a flow of 1 here, and a flow of 1 there, which gives me a max flow of 4. Let's consider a very similar graph or flow network to that one. Same vertices, same edges, and same flows except for one additional edge. So we'll have the same capacities, and on this additional edge we'll have a capacity of 1. Well, look at this now. You can say flow 4 there, 3, 1, 1, and 2, for a total flow of 5, a flow value of 5. Now let's make sure it obeys conservation. So let's look at this vertex here. With the flow coming in is 4. Flow going out is 3 plus 1 equals 4. How about this vertex? Flow coming in is 1 plus 1, 2. Flow going out is 2. It obeys conservation, so we're good. Now, what I have not given, and what I'm not going to give, is an algorithm to do that. The Ford-Fulkerson algorithm is going to give it to us, but we're not going to have time to go over that. However, there is a very important and fascinating property that comes out of this that we talk about a lot. It's called max flow min cut. Now, what do we mean by this? The max flow is equal to the min cut where min cut is the capacity of a cut that separates S and T. Okay, so the first thing we need to understand is what is a cut. So suppose we have some network, looks something like this. I don't know, I'm making this up. Okay, so there's my flow network. Let's just assume that it's a flow network. It obeys all the properties. I can cut this like so. And so what I've done is I've separated the graph into 2 components, that component and that component. One component contains S, the other component contains the sink, and I've made the cut. So I could do the same thing with I could make a cut that looks like this, or I could make a cut that looks like this, or I could make a cut that looks like this. I cannot make a cut that looks like this. The reason is I've now cut it into two components, that's true, but S and T are in the same component. So I must separate S and T. Okay, so now let's look at the theorem again. The max flow is equal to the min cut, where the min cut is the capacity of the cut. So let's talk about what the capacity of a cut is. So if I have S, and let's just do something very simple. Let's see, 1, 2, 3, 4. So here are my capacities. Let's make a cut, say here. The min cut is the capacity of is the sum of the capacities of the cut edges, 3 plus 1. If I made a cut that looked like, say, this, then the capacity is 2 plus 4 equals 6. That would be the min cut. Or if I make a cut that looks like this, it would be 3 plus 2 would be the min cut. Now, let's see the theorem in action. The max flow is equal to the min cut. Here is a flow network. And let's say we have the flows here. This is the flow network we had before. And so let's look at some cuts. Let's look at this cut here. This cut is equal to 5, that min cut. Or not, it's not the min cut, it's just a cut. It's the capacity summed together are 5. Okay, let's look at, say, this cut here. Let's see, capacities, 4 plus 2 is 6. Let's look at this cut here. And oh look, there's 4. And if you look back, we saw that we could come up with a flow of 4. So these are equal, and it turns out that this right here is the min cut. The only other possible cut on this graph is this one here, and that is equal to 5. So we find the min cut. One way we could do this is just to look at all possible cuts, but we'll see with the next example that that would be prohibitively expensive. We're going to need an algorithm to do it. So let's look at the second graph we looked at just a minute ago, where we added an edge. So we have 4, 3, these are the capacities, 2, 1, and then we added this edge right here. Let's look at it, and remember that we found a flow of 5. So let's look at a couple of cuts. Let's look at this cut here. This cut is equal to 7. It's the sum of the capacities at the cut edges. This cut right here is equal to 5. It turns out that that is in fact the min cut. There is an efficient algorithm to do this. We're not going to go over it, but this is a very important problem that's used all the time in lots and lots of different applications, flow networks.